Hi, I'm Drlica-Wagner, and I'm coming to you from Chicago, Illinois, in the United States. And today I'm going to be talking about small galaxies and what they can teach us about the fundamental nature of dark matter. So this is work that has been done with the Dark Energy Survey collaboration, who you can see part of here. DES is a collection of about 500 scientists spread around the world. And this is one of our most recent in-person meetings, which was a few years ago at this point, which took place in Campinas, Brazil. The work that I'm going to be talking about is a collection of effort from a number of people within the DES collaboration. So this talk is going to cover an introduction to cosmic probes of dark matter, searches for the darkest galaxies and results over the last couple of years, and then how we can use those observations of the faintest galaxies to constrain the properties of dark matter. And then I'll finish off with a little look forward to some of the perspectives for going below the threshold of galaxy formation. So I think this should be well known to most people at this workshop, but dark matter makes up roughly a quarter of the matter energy density of the universe, and there's robust empirical evidence for its existence from a number of astrophysical and cosmological probes, ranging from individual galaxies, and in fact, the small galaxies that I'll be talking about more here are some of the most dark matter dominated objects in the universe, all the way up to the cosmic microwave background. In spite of this robust evidence that we have from astrophysics, we still know relatively little about what dark matter is, its fundamental composition, and there are a wide range of different particle and macroscopic candidates to make up the dark matter that we see in the universe. The goal of this talk is really to try and use the distribution of dark matter to try and teach us something about the composition of dark matter. So a nice way to phrase this is in terms of the matter power spectrum, which has been robustly measured on scales roughly comparable to the size of the observable universe, down to small scales, roughly the size of our Milky Way galaxy. And over this wide range of scales, the observed matter power spectrum is robustly consistent with the lambda CDM model of cosmology, which includes cold collisionless dark matter. However, if you take the matter power spectrum to higher wave numbers or smaller scales, the observational data becomes more sparse and less constraining. And so it's still possible to fit the observed matter power spectrum with dark matter models that produce measurable differences from the CDM model. And some examples of this are warm dark matter that interacts in the early universe with protons and thus is able to exchange energy, or fuzzy dark matter, which is an ultralight particle that is delocalized on the scales of the smallest galaxies. Another way to visualize this is in terms of the clustering of dark matter in the late-time universe. So on this slide, I'm showing two sets of simulations. On the top are a set of simulations that were seeded with the same initial conditions, but on the left-hand side, it used a cold dark matter power spectrum, and on the right-hand side, so warm dark matter power spectrum, which suppresses power at small scales. And you can see in the late-time universe, this results in a dearth of small structures around Milky Way-sized galaxies. On the bottom is just another example where on the left-hand side is the usual cold collisionless dark matter model, and on the right is a model where dark matter is allowed to have some self-interaction, some scattering, and thereby distribute energy, distribute heat throughout a halo. And you can see that there are, again, noticeable differences in the distribution of dark matter on small scales in the late-time universe. In this plot, it's actually the density profile of dark matter more than the subhalo abundances that change. But the takeaway point from models like this is that we can learn about the fundamental makeup of dark matter by measuring clustering on small spatial scales. In other words, the particle physics that's governing dark matter has measurable effects on the smallest structures that we can observe in the present day universe. Of course, our universe is more complicated than just dark matter, and in particular, the baryons that make galaxies such interesting things to study also alter the small scale structure of dark matter in the late time universe. And this can happen both by suppressing the formation of galaxies in small dark matter halos and by disrupting those subhalos through tidal interactions dominantly with the disk of our galaxy. And this is a really interesting time to be studying the smallest galaxies, because cosmological simulations have been able to somewhat recently start to robustly include the core elements of baryonic physics to form realistic galaxies on scales comparable to the size scale of the small galaxies that we see around the Milky Way. And the real goal of sort of this domain of cosmic probes of dark matter is to be able to robustly model both the dark matter physics and the baryonic physics of galaxy formation and disruption at the same time. So there are a number of probes, observational probes of small scale structure of dark matter. On the top, I'm showing two probes that both rely on dark matter halos to be populated by baryons. These are the Milky Way satellite galaxies, which form in the center of small dark matter halos and are observed around our Milky Way galaxy. The Lyman alpha forest, which is observations of gas and small dark matter halos along the line of sight to distant quasars. On the other hand, on the bottom are two probes that don't necessarily rely on dark matter structures hosting baryons. One is Milky Way stellar streams, which are very fragile systems of stars in the halo of the Milky Way. And these systems can actually be tidally heated and perturbed by passing gravitational influences such as dark matter subhalos, whereas strongly lensed systems also probe the distribution of matter directly, and thereby are sensitive to dark matter substructures that may or may not host baryons. So this slide has also been divided between near field and more far field probes. And in this talk, I'm going to focus on the two topics on the left, the Milky Way satellite galaxies and stellar streams. So moving on now to the search for the darkest galaxies. So in the framework that we've been talking about so far, the picture you can have in mind is that our Milky Way galaxy lives in the middle of a large dark matter halo, which is not smooth, but rather hosts its own subhalos, these clumpy distributions of dark matter. Those dark matter subhalos themselves host galaxies, with the larger galaxies hosted by the larger subhalos. So in this case, this is the Large Magellanic Cloud, the largest satellite galaxy of the Milky Way. Whereas the expectation is that the smaller subhalos, at least up to a point, should host their own small galaxies. So the question we've been asking over the last few years is, how can we detect those very small and very faint galaxies that would inhabit the smallest probable dark matter subhalos? And the procedure, there are several procedures, but the basic idea is pretty well expressed by the slide. So you start with a catalog of stars, and this is because you're actually detecting these satellite galaxies through their resolved stellar populations and not from the integrated light. So you start with a catalog of resolved stars. This is dominantly Milky Way foreground stars. And so to clean out those Milky Way foreground stars, you can use things such as proper motion, but more conventionally, or over the last 10 years, we've used color magnitude selection filters, which are tuned to select the old metal poor and distant stellar populations of these faint dwarf galaxies in the halo of the Milky Way. So if you apply this color magnitude filter, you're left with a filtered distribution of stars, where I hope you can start to see an overdensity of stars appearing here in the lower right-hand part of this panel. And if you then convolve that catalog of stars with a spatial kernel, you can see the overdensity there is popping out much more prominently, and this is in fact one of the ultra-faint dwarf galaxies that was discovered in the Sloan Digital Sky Survey. So up until SDSS began, we were discovering satellite galaxies around the Milky Way in ones and twos, sort of by chance. Once SDSS started, we had a large area, deep and well-calibrated, very uniform catalog of stars over a large area of the sky. And this allowed us to apply the statistical techniques similar to the one on the slide before to detect these resolved stellar systems in the halo of the Milky Way. And this is what's responsible for the rapid increase in the population, the cumulative number of satellite galaxies around the Milky Way. In addition, we could use the Lambda CDM model with some relatively simple prescriptions for how galaxies populate dark matter halos to predict what the expected number of satellites would be once the next generation of surveys turned on. And the Dark Energy Survey, which started taking data in 2012, 2013, came along and largely followed through on the predictions that were made prior to its data taking, the start of its data taking. So you'll notice here that there's another strong uptick in the number of galaxies. DES is a smaller area of the sky than SDSS, but it also goes much deeper, and it also happens to be located close to the Large Magellanic Cloud, which I mentioned before is the largest satellite of the Milky Way, and now appears to have pretty clearly brought its own population of satellite galaxies into the Milky Way halo with it. So both of these facts are responsible for this sharp upturn. You can also notice that there are two kinds of dots here. So each one of these represents an ultra-faint satellite system, but only the red-colored filled circles are systems where we have measured the dynamical properties of the stars in those systems and confirmed that those systems are indeed dark matter-dominated galaxies, rather than the alternative, which would be baryon-dominated star clusters. So the open circles look very much like dwarf galaxies. They look very much like the dark matter-dominated systems from the photometric perspective. So morphologically, they're very similar sizes, ellipticities, distances, but we haven't yet been able to confirm that they're dark matter-dominated. That is largely because in order to fill in one of these circles, it takes aboard 2 nights on a 6.5 meter telescope with good weather in order to measure enough radial velocities of the stars in these satellites to be able to measure their dark matter content. Of course, that doesn't stop the photometric surveys from finding more of these systems. And since the surge of DES discoveries in 2015, there have been a fairly constant and steady stream of satellite galaxies and satellite systems discovered in data from surveys like Pan-STARRS, Hypersuprime-CAM, ATLAS, DCAM surveys outside of DES, as well as space-based astrometry and photometry from Gaia. And in general, we're discovering systems that are more distant, fainter, and more diffuse than those systems that were discovered in SDSS. Of course, just having a catalog of objects is not enough to do a rigorous systematic comparison to predictions from simulations. What you need is to also understand the satellite galaxies that were not detected due to the limits in your survey sensitivity. And so in order to do this, we initiated the 2020 Milky Way Satellite Census, which was choosing 2 of the surveys, the Dark Energy Survey and the Pan-STARRS PS1 survey, which cover 75% of the high latitude sky, and to use those surveys to systematically assess the sensitivity of current searches. And so combining these two surveys, we cover most of the sky. And in addition to recovering the vast majority of the known satellites, we also embed simulated satellite galaxy systems into our data set and run the same detection and recovery algorithms to be able to assess our efficiency and our survey selection function. So this tells us, as a function of galaxy size, luminosity, and distance, how likely it is for us to have detected that system. We can then combine this rigorous estimate of the survey selection functions with numerical simulations and a prescription for how galaxies map onto dark matter halos to build a forward model that allows us to generate mock catalogs of satellite galaxies. So we start with a set of dark matter only simulations here. These simulations importantly include an analog of the Large Magellanic Cloud, which, as I said before, likely brought in its own satellite galaxy population. Our model for mapping galaxies onto these dark matter subhalos includes a number of parameters such as the slope of the luminosity function, the effects of baryons in disrupting satellites, the scatter in galaxy properties as a function of halo mass, and additionally the size of satellite galaxies. And each of these model parameters is able to be fit to the observed data. And the way we do that is by choosing a set of model parameters, applying these to the subhalos in our simulation to generate simulated satellite galaxies, applying our survey selection functions, which tell us whether or not a satellite galaxy was detected, and then comparing that mock catalog of detected objects to the real catalog of detected objects, we can calculate a likelihood that includes effects such as the radial distribution of satellites, the angular positions of satellites, their sizes, and their luminosities. And so that likelihood compares our mock catalog and how well it models our observed catalog. And then by going back, we can change the galaxy halo model parameters and generate another mock set that can agree better or worse with our observed data. And by running an MCMC, we can then fit these different parameters of our galaxy halo connection model. And the result is that the best fit values of this model are completely consistent with predictions from the Lambda CDM model, including reasonably rigorous extrapolations of galaxy formation models that were fit at higher mass scales. And so while we do our fit directly on the ultra faint satellites, that fit agrees with what we would find at higher mass scales. And in addition, it agrees pretty well with predictions from hydrodynamical simulations, which are from first principles generating galaxies within dark matter subhalos. And so one of the main takeaway points of this plot is that there's no evidence for any kind of missing satellite problem around the Milky Way once you take into account these effects such as satellite disruption and the galaxy halo connection. Of course, we're not the only group doing this, and there are a number of papers that have come out over the last couple of years that are implementing various different models for fitting the observed satellite galaxy population to predictions from Lambda CDM. And in general, they're all agreeing on the takeaway point that Lambda CDM plus galaxy formation is able to accurately model and predict the satellite population that is now observed from around the Milky Way. Okay, so now with a good model of Lambda CDM and a good fit to Lambda CDM in hand, we can look to constrain alternative dark matter models from the observations of dwarf galaxies. And so the idea here, returning to the matter power spectrum, is that we can impose deviations to the matter power spectrum that come from the various physics that governs our alternative dark matter models. Those alternatives to the matter power spectrum then produce different sets of subhalos. They'll provide a different distribution of subhalos as a function of subhalo mass. We call this the subhalo mass function. So this is essentially a counting of subhalos in simulated galactic halos. And as you can see, these models, so warm dark matter or dark matter that scatters with baryons or fuzzy dark matter, all introduce suppressions in the subhalo mass function. So there are fewer low mass dark matter subhalos than would be predicted by CDM. And since we know that the CDM model is doing, or we have shown that the CDM model does a good job of producing the observed satellite population, as you suppress the number of low mass dark matter subhalos more and more, you'll lead to a larger and larger mismatch with the observed satellite population. And so we can go back to our process of fitting the observed satellite galaxies to our dark matter model and our galaxy formation model. But now we add another free parameter to this fit, which is the suppression scale of the dark matter subhalo mass function. And what happens when you do that is that you can basically take that subhalo mass suppression to the limit at which it is in tension with the observed satellite population within any arbitrary confidence level limit. And what we find is that at 95% confidence level, you can constrain thermally produced warm dark matter to have a particle mass of greater than 6.5 keV, which leads to a suppression in the subhalo mass function that looks something like this relative to CDM. So a very similar procedure can be applied to a wide range of different dark matter particle physics models, which each introduce a suppression to the subhalo mass function. And just highlighting some of them here. Since this is a short talk, I don't have time to go through all of these, but just focusing on one, which is an effective field theory model where there is some interaction cross-section between dark matter particles in the standard model. And this one is especially interesting because the observations of satellite galaxies are actually able to constrain a cross-section that is in the same parameter space as the direct detection experiments, such as LZ, Lux, Xenon. And so the idea here is that because you have some collisional cross-section between baryons and dark matter, that's able to exchange energy in the early universe and has a very similar effect to warm dark matter, and thus introduces a very similar suppression in the matter power spectrum at small spatial scales. Okay, coming to the last topic here. So all of the study that I've shown you so far depended on being able to produce observable galaxies in dark matter subhalos. Of course, the CDM model predicts that that the distribution of dark matter subhalos continues to much smaller scales. So the dwarf galaxies are found to populate subhalos in the range of upwards of 10 to the 7 to 10 to the 8 solar mass halos. Below that limit, galaxies are not expected to form due to the fact that it's impossible for those small, very small dark matter halos to retain their baryons through reionization. So the ultimate test of the CDM model will be the measurement of completely dark matter subhalos. And so I wanted to talk about one way that we could potentially detect these dark matter subhalos without any baryons, and that's directly through their gravitational influence on other dynamical systems around the Milky Way. And so as an example of how you can do this, I like to use a somewhat familiar example, which are the shepherd moons around Saturn. So this is a little shepherd moon. These are the rings of Saturn. And you can see that as this moon goes around Saturn, it actually introduces gravitational perturbations in the rings of Saturn. And so even if you couldn't see this small moon, you would be able to know that there was some gravitating object present here just by measuring the gravitational perturbations in the rings themselves. And so this basic concept is exactly what we are going to try to do, and there are several groups that are actively working on this right now. So instead of using the rings of Saturn, we're going to use the tidally disrupted remnants of dwarf galaxies and star clusters. These are called stellar streams. They're very dynamically fragile systems, since the stars have been tidally stripped and are thus unbound to the progenitor system. And that makes them very sensitive to determining both the smooth dark matter halo profile and any lumpiness or substructure in that halo. And so the way that we search for these is very similar to how we search for satellite galaxies. So they are also old metal core stellar populations. And so in this slide, I'm showing the color magnitude diagram for an old globular cluster in the DES footprint, and a selection window that we're just shifting across this color magnitude space as we walk out in distance. And you can see that as the filter matches the isochrone, the signal from the globular cluster increases. And so you can then apply the same procedure over the entire Milky Way footprint. So this is 5,000 square degrees in around the southern galactic cap. And what's happening here is that I'm passing this filter through the distribution of stars from DES and extracting old metal core systems in the halo of the Milky Way galaxy. And you can see these prominent linear features coming up, crisscrossing the DES footprint and crisscrossing the halo of the Milky Way galaxy. And these are the stellar streams that have been tidally disrupted through the influence of the Milky Way galaxy. So the next step is to try and look for perturbations in these streams, either the overall dynamical heating, which will occur from multiple impacts, stochastic impacts from dark matter substructure in the halo of the Milky Way, or individual large gaps and non-uniformities in the stars in these streams. And so this is a cartoon example for one of the streams, Palomar 5. This was another northern hemisphere stream, and there have been measurements that show that the distribution of stars in the stream are not uniform as would be expected from the most simplistic model of stream formation. However, this is a single stream, and it's now well known that there are other perturbers that can introduce wiggles and non-uniformities into streams, such as baryonic perturbers in the outer halo, giant molecular clouds, globular clusters, and the bar of the Milky Way itself. So what you really want to do is try and do this study on a population of streams to see whether all streams are sort of dynamically heated in the way that you would expect from dark matter subhalos. And so this process has started. Here are two more streams. This is the GD1 stream in the northern hemisphere, and this is the Atlas and Alika-Uma stream in the southern hemisphere, discovered by DES. And in both these streams, you can see this gap-like feature, sort of spurs and non-uniformities in the halos, in the stream stars. And here you can see almost a kink in the stream path, such that these streams were originally identified as two separate systems, but in fact the radial velocities show that they're one broken system. And so this is coming along from the observational side, as well as on the theory and modeling side. People are starting to combine observations. This is from Neil Bannock. Combine observations of satellite galaxies, as well as perturbations in streams, in this case from GD1 and Palomar 5, to try and constrain the presence of dark matter substructures, which in turn constrains the thermal mass of warm dark matter. And so this is my final slide, and it's just to get people excited about all the data to come. So the surveys on the top are all currently taking data. It's Gaia, DCAM in Chile, and then the AAT in Australia. So this is astrometric, photometric, and spectroscopic information that's coming down right now and is helping to improve our measurements both of the satellite galaxies around the Milky Way and the stellar streams. On the bottom are future surveys, the Roman Space Telescope, the Rubin Observatory, and DESI, which in the very near future are also going to extend our sensitivity to faint stellar systems, and thereby to measurements of the smallest dark matter substructures. Okay, thank you very much.